Good afternoon, everyone. It's Friday, September the 11th. This is period 5 AP Statistics, and we've downloaded some new notes. They are under the Chapter 2 resources on Canvas, and we're going to go ahead and get started with our learning targets. The first one says, find and interpret the percentile of an individual value in a distribution of data. And I'm just going to say, I know you guys are very familiar with percentiles because all of your standardized testing comes back in terms of percentile. So I know you've heard of it. I know you have a fair understanding of what it means. And we're going to go a little bit beyond what you know from your casual understanding of percentiles. And then we're going to have a second learning target estimate percentiles and individual values using a cumulative relative frequency graph. It's got a long name, but we're going to go ahead and get started, and you'll see what that long name actually means. So we're starting out with the continuation of our last set of notes from chapter 1. We were looking at our heights from the survey that you guys did the first week of school that some students did. Whoever was here that day did the survey. And you may remember this is the same dot plot that we used for that set of notes. So this time we're looking at how does my height compare with other AP statistics students, but we're looking at it in a slightly different way. And what I'm going to do is I'm going to just kind of run through the very beginning of it. Then we're going to break into breakout rooms, and you guys are going to fill out this first page, questions 1 through 4 in your breakout room. So let's just take a look at what we've got. We've got a dot plot. It says the dot plot below represents a random sample of the heights of 20 AP Stat students to the nearest inch. And oh, it's not 20, it's actually 15. So typo there, fix that. It's 15, that's how many dots we have. And so this is the dot plot that we did on Statlet last week. Not sure if you remember that, but we did. And then these are the summary statistics that Statlet came up with. So this was a combination of both the period 1 and the period 5 students. Once again, it was just whoever was there. So it says, describe the distribution. I'm just going to remind you when you do that, you're looking at your TPSu6e, okay? And you want to make sure that you describe things in context, meaning explain what it is. Don't just use numbers without explaining. So next we have some information about Isabella that we didn't know before. We know Isabella's height, and then you're going to answer part B based on your own personal height, all right? Then you're going to complete the table based on the information that's in the dot plot. And last of all, you're going to create the cumulative relative frequency graphs. And I'm just going to give you a little bit of instruction here. What you're going to do is you're going to graph on your horizontal based on those numbers, the right-hand side of the bar, and the other in the other direction, the vertical axis is going to be the cumulative relative frequency. And we'll go over to see what our grid looks like. Cumulative relative frequency. This 100 represents 100%, okay? So all of those numbers are percents, and always the cumulative relative frequency goes up to 1.0, which is the same thing as 100%. Another thing that I want to just mention while we're here is it starts at 0. So that means if you have zero, if you don't have 0, I should say, in this category, then it's going to be on the left-hand side, it's going to be 0 anyway. If you don't know that part of it, don't worry about it. When we get back together, we'll see. But the cumulative relative frequency, remember, relative frequency is, or this whole graph is actually going to give us, there we go. This is going to give us percentile. So we said we were going to talk about percentiles. We are going to talk about percentiles. You guys are going to be able to do the whole first page in roughly 4 or 5 minutes. So I'm going to see you back in about 5 minutes. And number 1, everybody should have been okay describing the shape, left skewed, possibly bimodal, is the way that I saw it. You might have seen it as unimodal, looking at 70 as the only peak, and then approximately symmetric. That's fine if you saw it slightly differently than the way that my eyes saw it. It is not a problem. And the reason is sometimes there's a little more room for interpretation than other times in this particular data set, because we just don't have that many pieces of data. We can see that we have what could be interpreted as 2 peaks, or we could look at 74 and say, had it been 75, then it would have looked unimodal and approximately symmetric, okay? So if we had more data, we'd have a better sense of which one it is. So either one of those answers would be fine. Clear? Okay.
I wrote skew right though, because I thought there was a gap between 74 and 70, what is that, 8, 77?
77. And I don't actually think there is, I mean, there is definitely a gap, but I don't know why that would make that skewed to the right. So
Yeah, I think skew left is better, probably.
So we have one way that you can do it is I always say count columns. So that would be 1, 2, 3, 4, 5, 6, 7. And on the other side, 1, 2, 3, 4, 5, 6, 7, 8. So if you look at that as unimodal, it is, if you look at it that way, approximately symmetric, because 7 on one side, 8 on the other side. Slightly skewed to the left. Okay, so again, it depends on how your eyes saw it. What I'm more concerned about on this question though is that you make sure to do it in context. So based on the dot plot, the shape of the distribution of student heights, so notice the context there, student heights is is whatever you wrote down. There are suspected outliers at 62 and 77, and my fault, because that should have units in there. So let me see if I can scoot that over just a teeny bit and then say inches. So helping it be more in context. And then the center is the median height at 70 inches. So that's our SOC. And V, we have the IQR is 77 minus 76. We just showed how we got the number of 7 inches. You don't have to use the IQR, but now that you can go beyond range, you should use a different measure of variability or a different measure of spread. The other thing that I want to mention is if you said that it was approximately symmetric, you should have quoted the mean and the standard deviation. If you said it was some skew somewhere, you should have used the mean and the IQR. So just keep that in the back of your mind. You want to use the appropriate measures for the shape of the distribution that you've got. Any questions here? Okay. So the next one says, Isabella is 65 inches tall. Isabella, you did put that on your survey. And so what percentile is she at? And what percent of the heights are less than or equal to 65? This is how we're defining percentile. And so we found out that Isabella is in the 20th percentile. Of the students who responded to the survey. Then what is your height? So whatever your height was, you were gonna calculate the percentile of your height based on the dots that you see. How many are at your height or below? Josh, what was your percentile?
Oh, 6.66 or 6 repeating percentile.
Okay.
Or 15.
So what you would have done is you would have found yourself, so this is you, right? So how many are at your height or below you?
My bad. Oh, 100th percentile.
Exactly. So you would be at the 100th percentile.
My bad.
Okay. All right, Jacob, what was your percentile?
I have to change it now because I did the same thing Josh did.
Okay, got it. So if anybody else also didn't do it based on dividing by the total number of numbers, how many are below, at or below your value, then go ahead and fix it now if you need to. Okay, so I used 62 inches for my height. That's why it says 62. So nobody else should say that. That was actually a lie. I'm not really 5'2". I'm a little shorter than that, but I often lie about my height, just a little bit, like 1 inch either way. Anyway, okay, so my height is at the 7th percentile. Obviously, I'm the lowest, but notice that there's no way to be at the 0 percentile when you define it this way. The other way that percentile is often defined is how many values are below you, not equal to or below, but just below. And in that case, it's impossible to be at the 100th percentile, but it is possible to be at the 0th percentile. Okay, so just keep that in mind. Now, when it came to the table, this is what your table should look like. So your frequency is whatever it is. How many dots do you have over each of those different values? Then when it comes to, let's see, relative frequency, this is not actually relative frequency. This is cumulative. So let me just make that correction right here. This is cumulative frequency because we're accumulating it. And then what we do for cumulative relative frequency is we take the cumulative frequency and make it relative by dividing by the total number of numbers that we have. So we would say 0 out of 15 gives us that 0 percentile. 3 out of 15 gives us the 20th percentile. 9 out of 15 gives us the 60th percentile, and so on. Okay, so the cumulative relative frequency is the cumulative frequency divided by the total frequency. Any questions?
You could just add them up as you go, right? The percents, because it's all out of the same denomination. So can you, because you're just talking about the class, so you can keep adding the percents up.
You can.
Okay.
If you had done relative frequency and gotten what obviously I didn't do, but you would have had the percents there, you can add the percents. The only thing that you need to be a little bit cautious about is rounding. So that's the only thing I would say. Check your rounding as you go to make sure that you're not creating more round off error than you need to.
Oh, okay. So yeah, like for 93, instead of 93, I got 93.33. But that's fine, I'm assuming, right?
Yes, yes, just be aware of that when you're answering a question like that one. Okay, so then once you've done that, you are able to now create the cumulative relative frequency because you have that last column on the right-hand side. And so this is basically what yours should look like. And you put the blue dots on that right-hand horizontal value and then the vertical number, which is your cumulative relative frequency. And then I joined them up. So I made my blue dots first, and then I joined them up in red. And I just made a couple of notations. Where we have that steeper slope, where it's increasing more steeply, then that's where we know we have the highest frequency of values. And if you notice, it's between that, like what looks like 65 to 70 group, and that's where we do have the highest frequency. We have 6 there. So that's just a connection that you can make between the frequency table and then the interpretation of the cumulative relative frequency graph. Now the question A said Muskoken is 62 inches tall. Estimate and interpret the percentile she is at using the graph. So we start out at the 62 inches tall, so we started out on that horizontal. And if you use 61 because it said 61, it's not a big deal, that's fine. So what you're gonna do is you're gonna trace from the axis upward to the cumulative relative frequency curve. We call things curves, as you know, even if they're straight lines. And then we trace from there across to the axis. When we trace across to the axis, that gives us a percentile value or a cumulative relative frequency value. So you should have come up with some small number. Mine showed around 8. We're reading it with our imperfect vision. So yours should say 8 or lower, right? You might have said 4 percentile, 4th percentile, 5th percentile, something like that. Then the other question says, estimate and interpret the 80th percentile. So when it comes to the 80th percentile, what we're gonna do is we're gonna start on that vertical axis at 80. We're gonna trace across to the curve, and then we're gonna shoot straight down to our axis to be able to read the value off of that. And again, imperfect eyes, I read it as about 73. So 80% of this, and when we interpret, 80% of the student heights are at or below 73 inches.
So why did you draw a straight line and not a curve? Because isn't it going to change at different rates? Or do we just, because it's kind of vague in between, do we just do a straight line and kind of use that as an approximation?
That's the reason why. Yeah, we know, for those of us who have taken calculus, we know that the way that we interpret curves can be seen as an infinite number of straight little tiny segments, right? Or the derivative at every location gives us the slope, right? So instead of looking at it, and we're going to call it a curve because lines are curves, curves are not lines. So we're always going to call it a curve whenever we graph something, whether it's a straight line or not. But in this case, exactly for the reason that you said, Ryan, we don't actually know exactly what's going on between our bars. And so, I don't know if you can see it very well, but I drew kind of as if there was a histogram here. This would be a cumulative histogram. You want to think of it that way. And so there are bars there, but we don't know what goes on between the boundaries of our bars. So that's
Right.
we use that straight line to not make any assumptions.
Does a regular cumulative frequency graph, does that have the bars or does it just have the line or the curve?
This is the cumulative relative frequency graph officially it's a line. It's
Okay,
a
gotcha.
series of segments. So there is such a thing as a histogram, cumulative relative histogram, or we could just have a cumulative frequency histogram.
Gotcha.
Okay.
Makes sense. Thank you.
All right. So is everybody okay up to now? Okie dokie. So the next thing that we want to do is fill out our important ideas based on our learning targets. And the first learning target that we had was about percentile. And we saw that we're going to make an assumption. There are multiple ways to calculate percentile, but the way that we're going to interpret it is that less than or equal to. So this is going to be the percent of values that are less than or equal to a given value. Okay. The second learning target that we had was all about the cumulative relative frequency graph. And so we're going to have that horizontal and vertical axis like we're used to. Our horizontal is going to start at, or our vertical is going to start at 0, I should say. And it's going to end at 1, which we often call 100%. And this is the graph that allows us to estimate percentiles. So having said that, it allows us to estimate percentiles, I want you to think about what we learned about last time when we used this set of data, and that was the box plot. So we learned all about the Q1, the median, and the Q3 that are in our 5-number summary. And now we know that that means that the data is broken up in chunks of 25% each. So we're going to say that the quartile 1 is located, and notice it's called quartile. And then we have percentile. And so this idea is all about positioning, quartile, percentile. You could have a decile also. That would be breaking it up by tens. So this is the 25th percentile. Whoopsie. The median is the 50th percentile, and the Q3 is the 75th percentile. So one of the things that should kind of spark in your mind a little bit is, now that you know how to relate percentiles and the 5-number summary, you can also come up with the IQR using the cumulative relative frequency graph. And Vincent, you were in IB Math last year, right?
Yeah.
Did you see this last year?
We didn't really. We kind of, I think we glossed over it in like a lesson maybe, but we were never like tested on it or anything.
Gotcha. Okay, so I'm going to give you another quick breakout session so that you can work on these check your understanding questions. They shouldn't take very long. So let's see. What I think I'm going to do is, if we do 3 minutes to work and 5 minutes of break, that brings us back at what? 20 after? I have no idea if I did that right. That's 7 or 8 minutes. So roughly 20 after, okay? So I'm going to put you in breakout rooms, but also I want you to take a short break, walk away from the screen, get a glass of water. And when you get back, work on these questions in collaboration. That means cameras on and talking to each other. Uh-oh, I think we lost Zach. Zach, you're okay? All right, looked like you fell right off the screen. Very dramatic.
We're good.
Okay, all right. So I'll see you back in a few. 20 after. Okay, so we were able to see how we explained to Mrs. Munson about her daughter. Now let's take a look at, and there should be writing on your graph. So is there anybody who's willing to share, to airplay their work now? Zach, you want to give it a go?
Number 2.
Yeah.
Hold on.
So you're gonna click on share.
Yeah, I just had to get there. Trust. Can you see it?
Not yet. You have to swipe down. There you
There.
go. Okay, beautiful.
I did it. So I got that roughly 68% of phone calls lasted less than or equal to 30 minutes, and 32 lasted more than 30 minutes.
Okay. Okay. Those numbers should add up to 100%, right?
Yep.
Okay. And yours do, so that's good. And then estimate the Q1, Q3, and IQR.
So for Q1, I estimated roughly 14. Q3, I roughly estimated 33. And then the IQR, I did 33 minus 14 to equal 19.
Okay. So I only have one objection to your answers. Does anyone know what the objection is going to be?
No context.
I love that. Units and context. Beautiful. That's exactly what I was going to say. So that is something that I would say you need to add on to your work, Zach.
Okay.
Okay.
So like, just for example, 68% of phone calls lasted like that.
Right. So I'm just gonna show you. I answered mine, and I think I wrote this on somebody's commentary. To answer in complete sentences, it doesn't have to be a perfectly crafted sentence, but if you answer in complete sentences, often you're forced to put the words in that will explain the context of what you're doing. The other thing that I would always recommend is, as you are creating these answers, you want to make sure that you're showing where the numbers came from. So your numbers may be slightly different than mine. That's less of an issue than the context and the units, and then showing the work on the graph. So when you show it, you want to, again, on an AP exam, you're not going to have the ability to use a ruler. So you're going to use your ID card or your driver's license or whatever you've got in your hand. to draw that straight line to the graph from one axis and then over to the other axis. The arrow is the one that you're trying to find, and that's the indicator to the person who's looking at your work of what you did.
Wait, are we allowed to use outside material to create that line? Like, can we use like,
You can't.
is it legal to use like your ID card?
Well,
No, they're gonna arrest you.
you have your ID card. So you're allowed to have your ID card or your driver's license. You're not allowed to have a ruler.
But is it like in the textbook, like, oh, materials you may use, like you may use?
No, it's not specific, but I mean, it's just like,
But it's not.
you could use the edge of your calculator if you wanted to use it as a straight edge as well.
Oh, so it's like by default, it's not like against the rules, but it's not like.
Right, it's not explicitly you can, but it's not, it's something that you already have with you. You're not bringing in a ruler or anything like that. Okay. Okay, overall, big picture, does anybody have any questions about what we've talked about here? Okay.
Do we have to do the lines on the graph?
When you say the lines, do you mean indicating where you started and where you ended up on the two axes? Yes.
Yeah.
Yes, you do need to do that.
Okay.
Okay. This is like a way of showing your work, a way of showing your thinking. Okay. Anything else? All right, let's move forward then to the continuation of this lesson, which had we been on 45 or 50-minute periods would have been on a different day, but now it's on the same day. So find and interpret the standardized score, the z-score, of an individual value in a distribution of data. So before we were doing that position or the location of that piece of data within the distribution using the percentile, now we're doing that using the z-score. And describe the effect of adding, subtracting, multiplying by, or dividing by a constant on the shape, center, and variability of a distribution of data. So you may have seen exercises associated with the second learning target in other contexts. And I know I usually do it with my 9th graders. So what we're gonna do is we're gonna look at some fake data. And this lesson is called How Did I Do? How well did you do on the chapter 1 test? How well did you do relative to your classmates? So this is fake data. This is not representing you or period 1. And it says, here are the results of a fake random sample of 20 of the chapter 1 tests, along with a dot plot and summary statistics. So we have the raw data, the dot plot from the Statlet, and the summary statistics from the Statlet also. And then you have a series of questions that you need to answer, and I'm going to put you in a breakout room to be able to do that. And so what you're going to do is you're going to try to answer all of the questions on that page, okay? So everything on that page, and I'm going to give you 7 minutes to do that. All right, and I'll see you back in a few.
Because then when I had to guess the formula or whatever, I put absolute values in there. I thought it was always positive.
Yeah, so because we think of it as we know it's off of, and with standard deviation, we knew that we were just trying to find an average distance away from the mean, but it was not directional. So with z-score, it is directional. We are interested in knowing, is it above or below the mean? And think about it, you get your standardized test scores, you want to know that too. You want to know, how do you compare to the average student your age, or in, you know, if you're taking a specific AP class, how did I do against other AP Physics C students, for example? So you want,
I said the absolute value of the mean minus the number over the standard deviation.
gotcha.
So.
Yeah.
So the z-score can really tell you like if you're like a possible not really, but if you're a possible outlier, right? If you have a z-score of like 5, that's like probably gonna be an outlier.
Okay, so I love that you said that, Ryan, because if you remember when we learned about the 5-number summary, one of the things that we said was we can calculate the IQR, which meant that we now had a way to determine outliers, but that this is not the only way to do it. And it's not the only way to do it. We use that 1.5 times IQR, but the other very popular way of looking at outliers is outside of 3 standard deviations, either above or below the mean. And you may or may not know this, some of you probably know this, this is how they identify national merit students, is if you're outside that 3 standard deviations above the mean in any given year. So I know some of you were probably identified, I don't even know what they call it. What do they call it? Commended, and then finalist, and then winner, right? I think those are the right
When
ones.
does the school inform us of that?
It's coming soon. It'll probably be in the next month or so.
The deadline for the application is the 7th.
So it's roughly the 7th of October, and it comes very soon after that.
No,
So-
like the deadline to know, like how do you
I'm
apply?
pretty sure it's supposed to be this week, but North Broward.
Yeah, it was supposed to be Wednesday, but
Well, you know that it's got to be coming then. So the only thing that you need to do is make sure that you have it identified, you know, whatever your top school is or wherever you think you're going to go, that thing, whatever. I think you have to you have to switch it so that it's one top place so that they can get notified. But then later on, you can switch it to wherever. The other thing is, for any of you, I don't know if we talked about this or not, but anybody who's a finalist or a winner, you get what's called the Benequisto Scholarship. Yeah, and which is a game changer, total game changer. So something to be on the lookout for if you're in that 3 standard deviation above group. Okay, let's go back to our notes. We talked about Biff, who was below the mean. We know that. Anybody who knows that movie knows that Biff is the bad guy. Then we have Marty, who's the protagonist in the movie, so he's the good guy. And his score was above the mean, and he actually was in the 80th percentile. And because we have a nice, beautiful, round standard deviation of 10, that means that his 8 points difference divided by the standard deviation of 10 gives him 0.8 standard deviations above. So this is where that sign comes in. It ends up being a positive number.
Oh, would you rather be a decimal than a fraction? Because I said 4/5.
Definitely, let's go with decimal on this one.
Okay.
Because part of the reason is when you start to think of how many standard deviations, it's like using that decimal number helps our brain really understand the fraction better. So knowing it's 80, 0.8 standard deviations, 8/10, we know that that's 4/5, but that's kind of an easy one. So you can see where sometimes the fraction would be a little bit less straightforward, and the decimal will give us a little bit better understanding. Okay, so a z-score is defined as the number of standard deviations above or below the mean. So your formula should be value minus mean divided by standard deviation, specifically because we want the below the mean to have a negative and the above the mean to have a positive z-score. All good? Okie dokie. So Goldie scored a 98, and that means he is 1.8 standard deviations above the mean. So he's really a rock star. But with a score of 98, we would have known that anyway, right? Does anybody remember what the job Goldie was going for was? Did you guys remember that or not remember?
He's the
Who's
one who gave out
Goldie?
the flyers. They gave out the flyers for him.
Right. And there were billboards up and signs all over the place. Yeah.
Oh, Goldie for mayor. That's right.
Okay. All right. So what I'm going to do is if you turn the metaphorical page and we go on to the next page, we have some additional questions. There are 2 mathematical operations used when calculating z-score. So we're getting a little bit algebraic here. So I want you to break that down, and then you're going to do that math. So you're going to do first the subtraction that you have in the numerator. Then you're going to do the division that you've got with that denominator, and you're going to create some dot plots, 3 dot plots specifically. And so what I would like for you guys to do is try to get through all of this page, and I'm going to give you, let's see, 5 minutes to work on this. You should get really close, and I'm going to put you in breakout rooms for that. So I know you may not have had quite enough time to do everything on that page, but we're going to go through it as quickly as we can because our time is really running short. And so for those of us who don't have a period 7, your weekend is going to start in a minute. All right, so the first operation, of course, is that subtraction. And you guys can do that little subtraction where you're taking each value and then minus the mean, minus 80. So you end up with some negative numbers, some zeros, and some positive numbers. This is what happens when you do subtraction. Negative, 0, or positive. Those are the only choices. And we created a dot plot for the original score, and then we created a dot plot for the score minus the mean. And we noticed that what we see when it comes to the shape, center, and variability of the dot plots as we compare them is the shape stayed the same. The two dot plots look exactly the same. However, the center is shifted. So it's almost, you can take that entire data set and then shift it by 80 because you're subtracting 80. It makes sense that this would happen. And then when it talks about variability, any measure of variability is also going to stay the same. If we look at IQR and we look at standard deviation and we look at range, the reason that it stays the same, all the measures of variability, is because the dots are exactly as far apart as they were before the subtraction. So we haven't increased or decreased the distance between them. The next operation that we do is division, when we divide by the standard deviation. And we created another table of differences divided by, this time, the standard deviation. And then we created another dot plot. And then we want to compare that to the original 2. And what we see is it looks pretty darn similar. However, the spread, or the difference, the distance between those points, you can see before we were going from 60 something to almost 100. And now we have from -2 to +2, basically. So the distance got super compressed. And how much did it compress, you might ask? And the answer, of course, is in the number that we divided by, that standard deviation. So it was a divided by 10 kind of relationship. So what did the center end up being? The center ended up being 0, and the new standard deviation ended up being 1. Is this clear so far?
Yeah, but I don't really get what's the importance of, like I understand you're showing the relationship, but what's the importance of that graph, the graph of the standard, the graph of the z-scores? Like, is that
Z-score is to help you have an understanding of what it means to standardize data. Anytime we standardize data, and it doesn't matter what the shape of the data is, anytime we standardize any kind of data, we're going to end up with a distribution where the mean is 0 and the standard deviation is 1. This is what happens. We start out with original data, we standardize the data, and it's on a graph, but with a different scale now.
also, no matter what, the mean's going to be 0?
When
For
we standardize, yes.
when we standardize.
Yes. So when we convert everything to z-scores, we've got a mean of 0 and a standard deviation of 1. Now, typically we use this more than anything else with normal distributions. And for those of you who took AP Psych, you are familiar with the normal distribution, and possibly from pre-calc honors as well. However, we're going to look at it, some things in common with the way that you've looked at it before. But in addition to that, we're really going to look heavily into the area under the curve, using algebra only, using z-scores. Okay, so no calculus in this statistics class.
Wait, can we use calculus if we want to?
You can if you want to, but I'm not going to teach it that way.
Okay, yeah, but it might be easier to, right?
What we're going to do is pretty easy. Don't
Oh.
worry.
Pretty straight lines.
It's
So
not going to
no
be bad.
problem.
You won't say, oh man, I wish I could use calculus. You won't ever say that. And then when you take
Ryan will. He loves calculus.
when you take statistics with calculus later on, you're going to be like, oh, this is just as easy as it was using algebra. So you're going to be fine either way. Anyhow, what's the punchline? The punchline is number 8, where we've summarized what happens. When we add or subtract the same value that we called A to each number in our data set, what ends up happening is the shape stays the same. There is our number A. The center gets shifted by the value of A, the number that we added or subtracted, and the variability stays the same because the distance between the points does not change. However, when we multiply or divide by some number, and we'll call this number b, each value, either multiply by b or divide by b, the shape stays the same. So the appearance stays the same. However, the center changes. So the center always changes. Notice that. And this time the variability also changes. And it's either the multiplied by or divided by value. So question number 9 comes up. What is the mean and standard deviation of the distribution of z-scores? Will this be true for any distribution of z-scores? And I kind of gave that away already. That is going to be true for any distribution, regardless of the original shape of the parent population or of the sample that we took. This is actually a great stopping point. Unfortunately, we didn't have time to reflect against our big ideas with our learning targets. However, I am going to post that, and you have a check your understanding that I'd like you to work on between now and when I see you again. Okay?
Yeah, I just find that like really interesting that like when you standardize it, it like it makes like complete sense that like why you standardize it so you can get like a more even distribution.
You can get a distribution that you can understand a little bit better. You can
A
compare
little bit better, yeah.
two very different ones. It's kind of like creating a common denominator for distributions.
Yeah, because you know the mean and standard deviation are the same.
Okie dokie, everyone. Have an awesome weekend.
Thank you. You too.
See you again.
Bye. Thank you.
Have a nice weekend.
Bye.
Miss Gogan?
Yes. Hang on one
So-
second.